Section 1. How rock deforms. The Himalayas, the Rockies, the Andes, and some of the Earth's most majestic mountain ranges. Mountain ranges are visible reminders that the shape of the Earth's surface changes continuously. These changes result from deformation, or the bending, tilting, and breaking of the Earth's crust. Isostasy. Deformation sometimes occurs because the weight of some part of the Earth's crust changes. Earth's crust is part of the lithospheric plate that ride on top of the plastic part of the mantle called the asthenosphere. When parts of the lithosphere thicken and become heavier, they sink deeper into the asthenosphere. If parts of the lithosphere thin and become lighter, the lithosphere rises higher into the asthenosphere. Vertical movement of the lithosphere depends on two opposing forces. One force is the force due to gravity or weight of the lithosphere pressing down on the asthenosphere. The other force is the buoyant force of the asthenosphere pressing up on the lithosphere. When these two forces are balanced, the lithosphere and the asthenosphere are in a state called isostasy. However, when the weight of the lithosphere changes, the lithosphere sinks or rises until the balance of the forces it reached again. Movements of the lithosphere to reach isostasy is called isostatic adjustment. One type of isostatic adjustment is shown in Figure 1. These isostatic adjustments occur. Areas of the crust are bent up and down. This bending causes rock in the area to deform. First picture. When the gravitational force equals the buoyant force, the lithosphere and the asthenosphere are in isostasy. As erosion wears away the crust, the lithosphere becomes lighter and is pushed up into the asthenosphere. As erosion continues, the isostatic adjustment also continues. Figure 2. Mount Kahindin in Baxter State Park, Maine, has been worn down by weathering. As the mountain shrinks, the crust underneath it is uplifted. Mountains and isostasy. In mountainous regions, the isostatic adjustment occurs. In mountainous regions, isostatic adjustment constantly occurs over millions of years. The rock that forms mountains is worn away by the erosion action of the wind, water, and ice. This erosion can significantly reduce the height and weight of the mountain range, such as the one shown in Figure 2. As the mountain becomes smaller, the surrounding crust becomes lighter, and the area may rise by isostatic adjustment is called uplift. Deposition and isostasy. Another type of isostatic adjustment occurs in areas where rivers carry large amount of mud, sand, and gravel flow into larger bodies of water. When the river flows into the ocean, most of the material that the river carries is deposited on the nearby floor. The added weight of the deposited material causes the ocean floor to sink by isostatic adjustment in a process known as subsidence. This process is occurring in the Gulf of Mexico at the mouth of the Mississippi River, where a thick accumulation of deposited material has formed. Glaciers and isostasy. Isostatic adjustment also occurs as a result of the growth and retreat of glaciers and ice sheets. When large amounts of water is held in glaciers and ice sheets, the weight of the ice causes the lithosphere beneath the ice to sink. Simultaneously, the ocean floor rises because the weight of the overlying ocean water is less. When glaciers and ice sheets melt, the land that was covered with ice slowly rises as the weight of the crust decreases. As the water returns to the ocean floor sinks. Stress. As the Earth's lithosphere moves, the rock in the crust is squeezed, stretched, and twisted. These actions exert force on the rock. The amount of force that is exerted on each of the area is called stress. For example, during isostatic adjustment, the lithosphere sinks and rises atop the lithosphere. As the lithosphere sinks, the rock in the crust is squeezed in the direction and the direction of stress changes. As the lithosphere rises, the rock in the crust is stretched and the direction of the stress changes again. Similarly, stress occurs in the Earth's crust when tectonic plates collide, separate, or scrape past each other, as shown in Figure 3. Figure 3 shows the three main types of stress. So we have compression, we have tension, and we have shear. Compression, the type of stress that squeezes and shortens a body, is called compression. Compression commonly reduces the amount of space that rock occupies. In addition to reducing the volume of rock, compression pushes rocks higher up or deeper down into the crust. Much of the stress that occurs at or near the convergent boundaries where tectonic plates collide is compression. Tension. Another type of stress is tension. Tension is a stress that stretches and pulls the body apart. When rocks are pulled apart by tension, they tend to become thinner. Much of the stress that occurs at or near divergent boundaries where tectonic plates pull apart is tension. Shear. The third type of stress is shear stress. Shear stress distorts a body by pushing parts of the body in opposite direction. Sheared rocks bend, twist, or break apart as they slide past each other. Shear stress is common at transform boundaries, where tectonic plates slide horizontally past each other. However, each type of stress occurs at or near all types of plate boundaries in various other regions of the crust too. Strain. When stress is applied to a rock may deform or change in the shape of the volume of the rock that results from a stress called strain. When stress is applied slowly, the deformed rock may regain its original shape. When the stress is removed, however, the amount of stress that the rock can withstand without permanently changing the shape is limited. This limit varies with the type of rock and the conditions under which the stress is applied. If a stress exceeds the rock's limit, the rock's shape permanently changes. Types of permanent strain. Materials that respond to stress by breaking or fracturing are brittle. Brittle strain appears as cracks or fractures. As Figure 4 shows, ductile materials respond by stress by bending or deforming without breaking. Ductile strain is a change in the volume or shape of the rock in which the rock does not crack or fracture. Brittle strain and ductile strain are types of permanent strain. Factors that affect strain. The composition of rock determines whether rock is ductile or brittle. Temperature and pressure also affect how rock deforms. Near Earth's surface, where temperature and pressure are low, rock is likely to deform in a brittle way. At higher temperatures and pressure, rock is more likely to deform in a ductile way. The type of strain that stress causes is determined by the amount and type of stress by the rate at which stress is applied to rock. The greater the stress on the rock is, the more likely rock is to undergo little strain. The more quickly stress is applied to rock, the more likely the rock is to respond in a brittle way. Folds. When rocks respond to stress by deforming in a brittle way, folds commonly form. A fold is a bend in a rock layer that results from stress. A fold is most easily observed where flat layers of the rock are compressed or squeezed inward. As stress is applied, the rock layers bent and folded. Cracks continue to appear in or near a fold, but most commonly the rock layers remain intact. Although fold commonly results from compression, it can also form as a result of shear stress. Anatomy of a fold. Folds has features by which they can be identified. Scientists use these features to describe folds. The main feature of a fold are shown by illustration 5. Let's go look at 5. So when we take a look at illustration 5, although not every fold is symmetrical, every fold has a hinge or limbs. Okay, so the hinge appears to be that middle area where it bends, and the limbs are the area that go down to the side. Like here, this would be the hinge, this would be the limbs, each side of that. The sloping sides of the fold are called the limbs. The limbs meet at the bend of the rock layers, which is called the hinge. Some folds also contain additional features. If a fold's structure is such that a plane could be sliced, the fold into two symmetrical halves, the fold is symmetrical. The plane is called the fold's axial plane. However, the two halves of the folds are rarely symmetrical. Many folds bend vertically, but folds can have many other shapes, as shown in the photograph of figure 5. Folds can be symmetrical. Sometimes one limb of the fold is more steeply than the other limbs does. If the fold is overturned, the fold appears to be lying on its side. Folds can have open shapes or can be tight as a hairpin. A fold's hinge can be a smooth bend or may come to a sharp point. Each fold is unique because the combination of the stress and conditions that causes the fold was unique. Types of folds. To categorize a fold, scientists study the relative ages of the rocks in the fold. The rock layers of the fold are identified by the age from the youngest to the oldest. An anticline is a fold which the oldest layer is in the center of the fold. Anticlines are commonly arch-shaped. A syncline is a fold which the youngest layer is in the center of the fold. Synclines are commonly bowl-shaped. A monocline is a fold in which both limbs are horizontal or almost horizontal. Monoclines form when one part of the Earth's crust moves up or down relative to the other part. The three major types of folds are shown in figure 6. This here is an anticline, this is a syncline, this is a monocline. Okay. Sizes of folds. Folds which appear as wave-like structures in a rock layers vary greatly in size. Some folds are small enough to be contained in a handheld rock specimen. Other folds cover thousands of square kilometers and can be seen only from the air. Sometimes a large anticline forms a ridge. A ridge is a large, narrow strip of elevated land that can occur near mountains. Nearby, a large syncline may form a valley. The ridges and valleys of the Appalachian Mountains are examples of landforms that were formed by anticlines and synclines. Faults. Stress does not always cause rocks to fold. Near Earth's surface, where temperatures and pressures are low, stress may simply cause rocks to break. Breaks in rocks are divided into two categories. A break along which there is no movement of the surrounding rock is called a fracture. A break along which the surrounding rock moves is called a fault. The surface or plane along which the motion occurs is called the fault plane. In a non-vertical fault, the hanging wall of the rock, in a non-vertical fault, the hanging wall is the rock above the fault plane. The footwall is the rock below the fault plane. So the footwall is here because it is below. The hanging wall is here because it is above the fault. Normal faults. As shown in figure 7, a normal fault is a fault in which the hanging wall moves downward relative to the footwall. Normal faults commonly form at divergent boundaries, where the crust is being pulled apart by tension. Normal faults may occur as a series of parallel fault lines, forming steep, step-like landforms. the Great Rift Valley of East Africa formed by large-scale normal faults. Here is a normal fault. A reverse fault. When compression causes a hanging wall to move upward relative to the footwall as shown in Figure 7, a reverse fault forms. A thrust fault is a special type of reverse fault in which the fault plane is at a low angle or nearly horizontal. Because of a low angle of the fault plane, the rock of the hanging wall is pushed up over the rock of the footwall. Reverse faults and thrust faults are common in steep mountain ranges such as the Rockies and the Alps. Here is a reverse fault, and here is a thrust fault. A thrust fault is a specific type of reverse fault. Strike-slip fault. In a strike-slip fault, the rock on either side of the fault plane slides horizontally in response to shear stress. Strike-slip faults got their name because they slide or slip parallel to the direction of the length or strike of the fault. Some strike-slip fault planes are vertical, but many are sloped. Strike-slip faults commonly occur at transform boundaries where tectonic plates grind past each other as they move in opposite direction. And these motion cause shear stress on the rock at the edge of the plates. Strike-slip faults also occur at fracture zones between offset segments of mid-ocean ridges. Commonly, strike-slip faults occur as groups of smaller faults in area where large-scale deformation is happening. Here is strike-slip. The San Andreas fault The San Andreas fault system stretches more than 1,200 kilometers across California and is a result of two tectonic plates moving in different directions. Size of faults. Like faults vary greatly in size. Some faults are so small that they affect only a few layers of rocks in a small region. Other faults are thousands of kilometers long and may extend several kilometers below the Earth's surface. Generally, large faults that cover thousands of kilometers are composed of systems of many smaller related faults rather than a single fault. The San Andreas Fault in California, as shown in Figure 8, is an example of a large fault system.